So after all our hard work about the meaning of slope and area for position and velocity time graphs, we're going to put this together to create a mathematical model of motion. This is the whole goal. Okay, there's a lot of examples in the real world where we can approximate things moving at a constant acceleration, like a rocket taking off, or a car skidding to a stop, or a ball rolling down a hill. All of these, the approximation of constant acceleration is valid, and so we can use what we've learned about velocity time graphs to, write some equations to mathematically describe this type of motion. Okay, so how do we get these equations? Well, they all come from this basic premise that going from position time, you can take the slope and get a velocity. To take the slope of the velocity gives you acceleration, and so on and so forth. Okay, so it's just ideas of slope and area that we're going to use to derive equations. Okay, so let's start with a simple one. Okay, so this is VI and this is this is VI and this is VF. Okay, so we have an object that starts off 5 meters per second and increases its velocity at a constant rate. Okay, so the first thing we can look at is acceleration is the slope. Okay, so we can use numbers. So here acceleration is equal to, this point here is 15, so 15 minus 5 over 10 minus 0 gives us an acceleration of 1 meters per second squared. Okay, but we can also do this with numbers. So what was the 15? The 15 was the VF. What was this 5? This 5 was the V minus VI over TF minus TI. Okay, and so this is change in velocity over change in time. Okay, so we get our first equation, which is A times delta T is equal to VF minus VI. Okay, so this is an equation. We'll call this equation 1. Okay, so let's now look at area. We know that if we take the area of under a velocity time curve, we get displacement. So to do that, though, we have to divide this into two parts: one big triangle and one big rectangle. Okay, we'll call the rectangle area 1 and we'll call this triangle area 2. So the total displacement under that curve will be area 1 plus area 2. Okay, so what's area 1 equal to? Well, area 1 is equal to the height, which is 5, times the width, which is 10. But if we wanted to do this in letters, area 1, so the 5 is the V initial, times 10, which is the delta time. So area 1 over here is just V initial times delta T. Okay, let's do the same thing for area 2. Area 2 would be 1/2 base times height, which would be equal to 1/2. The base is 10, and the height is, so the height would be this value right here, which is 15 minus 5, which is, okay, I'll actually put the 15 minus 5. So how do we do this in letters? We have area 2 is equal to 1/2. The base is just our delta T, that's our change in time, and the height is 15 minus 5, but in terms of letters, that would be VF minus VI. Okay, so our area 2 is 1/2 delta T times VF minus VI. Okay, so now we can, simplify this a little bit, because we see that VF minus VI is the same thing as A times T, so we can sub that in there. Okay, when we do that, we get delta X is equal to VI times, instead of delta T, we'll just put T plus 1/2 times T, and this would be A times T. We're just leaving at the delta T's. Okay, so when we simplify that, we get VIT plus 1/2 AT squared. Okay, and so this is our equation 2. Okay, And then sometimes we write this as VF is equal to VI plus AT. Okay, so that's equation 1. We're just rewriting this thing right here. And now if we were to put 1 and 2 together, so put 1 and 2 together, a little bit of algebra, we get VF squared is equal to V initial squared plus 2A delta X. You can do that as an exercise. Okay, so you're just kind of substituting time inside this equation. So the whole idea is we have 3 equations that model motion with constant acceleration. You cannot use these equations unless the motion is undergoing constant acceleration. And the idea is we have 3 equations, and each of these have some quantities that will be in the problem and some of them don't. So in this equation 1 has VF in the equation, it has VI, it has time, it doesn't have delta X, and it has acceleration. Okay, so equation 2 doesn't have VF, but it has VI, it has T, it has delta X, and it has acceleration. And in this case here, we don't have delta T, but we have all the other quantities. Okay, so depending on what the problem is, we'll be using different equations. So let's have a look here. Let's start with the first example. A skier is going at 8.2 meters per second when she falls and starts skidding down the ski run. After 3 seconds, her velocity is 3.1 meters. How long after she fell did she finally come to a stop? Assume that her acceleration was constant. Okay, so if we need to do a motion diagram, we're going at 8.2 meters per second for 3 seconds. And then after, so this is time is equal to 0 seconds, and then after time is equal to 3 seconds, she falls down and, nope, never mind, after 3 seconds her velocity is 3.1 meters per second. So she's always kind of slowing down. So she's going, and then she's always slowing down, and then comes to a stop. Okay, so how long after she fell? So what's the distance is what they're basically asking. No, what's the time? How long? So how long does this whole thing take? Okay, well, at the V initial here, we are going 8.2 meters per second. After 3 seconds, we'll call it V final, we're going 3.1 meters per second. And in this point here, we don't know what the speeds are, but we know the acceleration remains the same because she's slowing down at a constant rate. That's what this thing says right here. So what we need to find is the acceleration as she's falling down. And we have the V initial is 8.2 meters per second, and we know that the final velocity is 3.1 meters per second. Okay, and we also know that the delta time is 3 seconds. Okay, so we have to look in our list of equations, and we have A, V, I, VF, and delta T. And so which one of those equations have all those 3 variables? And we would say that's the first equation right here. So we'll take that equation, we say VF is equal to VI plus AT. VF is 3.1 is equal to 8.2 plus A times 3 seconds. Okay, when we solve for A, okay, using our calculators, we should be getting a negative acceleration because we're slowing down. And indeed, if you punch this into your calculator, you get an acceleration of negative 1.7 meters per second squared. Okay, but we still need to know the time of the entire trip. So what do we know about the entire trip? Well, we know the entire trip has an acceleration of negative 1.7 meters per second squared. We also know that the V initial is 8.2 meters per second. We know that the V final is 0 because she comes to a stop, and so we're looking for delta T. Okay, well in this case we can again use the same equation, but in this, so we have VF is equal to VI plus AT. But in this case, VF is 0, V initial is 8.2 plus A, which we now know is negative 1.7 times time of the entire trip. So this would be negative 8.2, that's negative, divided by negative 1.7 would give us the total time. And the total time, if you take 8.2 and divide it by 1.7, you get 4.8 seconds. Okay, if we quickly try the next one here, you'll get lots of practice doing this. But let's try another one. Number 2, a car is traveling east along a straight road at a constant velocity of 18 meters per second. After 5 seconds, so after the first, so it's going 18 meters per second, time is equal to 0, and then time is equal to 5. It's going at constant velocity. Okay, velocity doesn't change. But after 5 seconds, it accelerates uniformly, means at the same rate for another 4 seconds. So for the next 4 seconds, the distance gets bigger and bigger. Okay, so this is t is equal to 9 seconds now. When it reaches a velocity of 24 meters per second, the car proceeds with uniform motion for another 6 seconds. So it's going fast, so it's going super fast. At that point here, it's going 24 meters per second, and it proceeds at this 24 meters per second for another 6 seconds. Okay, so there's what is the total displacement during the trip? Okay, now because the acceleration changes throughout this time, we can't just take the equation and use like the velocity here and the velocity and the end, because during this time the acceleration is changing. So we have to break this down into 3 parts. First one will be this first part here when the acceleration is 0. Velocity initial is 24 meters per second, and the time of 5 seconds. Well, then we can easily find what the displacement during this time is. Okay, that would just be delta x is equal to vit plus 1/2 at squared. So this is the second equation, but acceleration is 0, so that goes to 0, and so we have delta x is equal to 24 times the time, which is 5 seconds. Okay, so then 24 times 5 gives you 120. And so the first 5 seconds, we've displaced 120. Now, how much did we displace in the next 4 seconds? Well, during the next 4 seconds here, we're accelerating. Okay, so this is very important. So acceleration is not 0. So we know the v initial at the start was 24 meters per second, because that's what was over here, 24 meters per second. Then we know the duration is 4 seconds. And it accelerates uniformly until it reaches, oh shoot, this thing was 18. This whole thing is 18 meters here. Apologies. So we will get 18 times 5. It's 90 meters. Shoot. Okay, so this would be 90 meters. So the v initial here is 18 meters per second, time is 4 seconds, and v final is 24 meters per second. Okay, and we need to find the displacement. Well, for this one we can use equation 3, which is that v final squared is equal to v initial squared plus 2a delta d. Shoot, we can't use this one because we need the acceleration. So first we need to find the acceleration using a different formula. So that's we need to use v final is equal to v initial plus a t. V final is 24. V initial is 18 plus a times t, which is 4 seconds. When you find acceleration, for that you get 6 divided by 4. So acceleration is 1.5 meters per second. So now you can use this equation to find the distance. Okay, when you do that, you get 24 squared minus, I'm going to do this all in one step, 18 squared divided by 2 A, which is 1.5. So you get a distance of 84 meters. Take your time to do this. I'm just trying to do this to show you quickly. And in the last section here, we're moving at a constant speed. So the V initial is 24 meters. Acceleration is 0. And time is 6 seconds. And so we want the displacement in the x. Okay, so we're going to use the same equation as here. So delta x will be equal to 24 times 6, and that's equal to 144 meters. And so the total distance, so displacement total, will be 90 plus 84 plus 144, because you have to add up all the displacements for each of the time intervals, and when you do that you get 318 meters.